We still got people coming in, so come in fast. Right, so how many software architects are in here? Not very many, like 3. How many security people are in here? Oh, there's 1, 2. What does that mean? Only on Thursdays? Yeah, that's good. It's Thursday, man. You're on. I got started in software security a long time ago. Basically, when this language that you might have heard of called Java came out. Anybody ever heard of Java in here? Right. So if you remember those guys that were breaking Java back in the early days, when some of you were probably 3, that was me and Ed Felton from Princeton. And it made me wonder why incredibly amazing developers and super wizard architects and the best programming languages people on the planet got it all wrong when it came to security, and what we could do about that. And you know what the answer turned out to be? The answer turned out to be that people like you, people who build stuff, are the people that are most important when it comes to security. It's not about network stuff. It's not about protecting the broken stuff from the bad people by putting a thing in between, like a firewall. It's not about antivirus crap, which makes your compiler not even work. It's just not about, protecting the broken stuff. It's about not making the stuff broken in the first place. So this was a fairly obvious idea, I thought. And let's see, I wrote this book called Building Secure Software in 1999. So it's like 19 years old, something like that. Almost old enough to drink on its own, but not quite, in the ridiculous United States. I think you guys can drink at 18 around here, right? Yeah, so it's old enough to drink on its own in Australia, that book. That's good. And we've made some pretty good progress in computer security since then. Still, maybe 80% or so of computer security stuff is network security, people talking about firewalls and all that jazz. But a good 20% now has to do with building security in the first place, and software security. Here's the real bummer. So we've made a ton of progress on looking through code for bugs. And we've made some progress in making languages that do not suck from a security perspective. Like C++ sucks from a security perspective. C sucks from a security perspective. Java, a little bit better. JavaScript, not really a language. You know how it goes. Oh, it's so easy. It's just like... I do want to share the fact that this is work that I'm talking about today, which was put together with a group of my friends from all these little places, so Twitter and Google and EMC and HP and Synopsys and whatever. And basically, here's the problem. There is a type of security defect called a flaw, which is a design level thing, not a code level thing. And flaws account for, in my experience, about half of the problems out there. The issue is that almost all of the stuff that you read about software security turns out to be about bugs, about things like SQL injection or buffer overflows in C or things like that, and not about flaws. And so today what I want to do is tell you what flaws are, and then tell you about a collection of flaws that we sort of came up with this group of people and how to avoid them. So this is really a talk about software architecture and about things that go wrong in software architecture that cause security problems. So it's not your sort of normal talk. We gathered a bunch of people together and we wrote a little report about this after just a little bit of bourbon, which was very good. And we actually got the IEEE to publish this thing under the Creative Commons. It's the first thing in the world ever published by the IEEE under the Creative Commons. I think they're still confused about exactly what we made them do, but that's good. And you can hit it at that URL. So there's a nice piece of work there that you can take, hopefully, and adopt to your own organization or your own way of thinking about software architecture. For example, the guys at Twitter took the top 10 pieces of advice that we have in here, and they changed their frameworks accordingly that they use in-house so that some of their patterns reflected the things to not to do. And that made a huge difference. Same thing at Google. So this work is actually fairly straightforward to port from hand wavy level to actual code frameworks if you do it. So first of all, a little bit of remedial work. What is a flaw? All right, so there are bugs. There's a list of some bugs. And there are flaws. And there's a list of some flaws. And of course, you can't really say there are only two kinds. There's sort of a continuum in between. But let's just pretend that there are two kinds. And now I want you guys to guess, what is the percentage of security problems that are caused by bugs and flaws, just percentage-wise? Anybody have a guess? Yell some stuff out. 80-20. Who said that? 80-20 which way? I don't know. This way doesn't make sense. 80 architecture, 20 bugs. That's very interesting. Wrong, but good guess. Anybody else? 80-20 the other way. Also wrong. Yes. You're just a math guy, so you don't get to answer. He said 50-50, which turns out to be right. And if you're a math guy, you might as well guess that one. It's right in the middle of the bell curve, right? Right. So my favorite answer of all time for this came at Qualcomm, where some guy said 60-60. Or maybe it was 70-70, I don't know. And it's like, wow, everybody moved away from that guy. They're like, oh, he can't really do math very well. But it turns out that maybe if it were 60-60, that means there are 20% more security problems than we thought in the first place, right? So maybe that's right. But I do want to make clear that the flaws kind, which account for a good half of the problems in my experience, are actually much harder to find than the bugs kind. And we've made a whole bunch of progress on the bug stuff. Like we can say things like, don't use getS. That's pretty easy. And then we can grep through our code looking for getS. And we'll find actual uses of getS. We'll find things in the comments that have nothing to do with getS. We'll find father begets son, which also has getS inside it. But we can grep for patterns, which is part of the way of getting across that syntactically, because of the way our languages are built and how our compilers work, we can look through code for bugs in a pretty straightforward fashion. Of course, there are ways that can get rid of false positives. We need to think about data flow. We can use taint analysis. There are all sorts of things that we can do to make our look for bugs more efficient. And there are all sorts of commercial tools that are available for looking through your code for bugs. The real question to ask is, why the hell do I have to buy a tool for that? Why doesn't the compiler just not let me do it? Or, why is that language so sucky? C#. Sorry, I got something stuck in my throat. So let me give you an example of a flaw. This is also pretty easy to describe. Okay, here we go. First flaw. Forgot to authenticate user. Nah, that's it. It's like, you're the guy who wrote the code is for you, you are God, you're allowed to do everything, it's great. Why authenticate anybody? Just be God, right? Doesn't that sound powerful? It's like chmodding your stuff 777 to make it work. That's not how to do it. I mean, yeah, that's not how to do it. So forgot to authenticate user is a good example of an easy flaw. Flaws are actually a thing in software security. You guys might not have heard of this system called the BSIM that I came up with about a decade ago. We actually just go to mostly big software houses and banks and people that produce tons and tons of code. About 600,000 developers are now covered by the work of the BSIM. And we ask them, what do you guys actually do for software security? And then we just keep track of that. What they do and what they don't do. A lot of firms do a lot of code review. They use static analysis tools. They have pretty sophisticated tooling and processes that they've set up to look for bugs and put them into their vulnerability pile or their bug tracking system or whatever, and eventually eradicate them. However, when you look at the thing about flaws, we look at architecture analysis, like how do we find design flaws, it turns out we're doing very, very poorly when it comes to BSIM data, like out there in the world. And the problem is that, you know, the main approach to security analysis at the architectural level is a bunch of smart guys in the room. Anybody ever done that one before? So, you know, basically you put a piece of software in the middle, a bunch of smart guys come, and then they criticize each other for a while, you know. And then somebody gets mad and quits and whatever, and then, you know, you find a flaw, maybe if you're lucky. But actually, you laugh, but we used to use that method, because if you want to find brand new flaws, you can't start with a list of flaws like I'm going to give you at the end of this talk when I finally get around to it. We're not going to, you know, you can't have a list, because the list is fine for finding things you already know about, known flaws, but what's not on the list? Unknown flaws. It's like the unknown unknowns. Some American concept. I don't know. Something totally ridiculous. Right? So if you want to find unknown unknowns, just put two architects in the same room with one pile of code and just film it. Seriously, just film it, and where they start saying, "Nah, that's not how it works." And actually, what we found is, instead of thinking about security scenarios when you're doing that work, it's actually much more powerful just to talk about your conception of how the system works versus somebody else who's extremely good, their conception of how it works, and see where you disagree, where there are ambiguities in the design or the spec or the way that you described your system is where you're going to find new flaws. So that's something that we can do. Now let me give you another couple of examples, or maybe just one. Here's an example. Anybody hear about this recent Facebook thing where like 90 million users got their stuff outed? Yeah? No? No one gives a shit about security? Damn. Okay, well, this is that problem. I mean, basically there was a nice little thing, the view as thing, and it looked fine all by itself, but the problem is the view as thing interacted really poorly with the video thing, and you put them together and it just caused a terrible security flaw. And you know what? Each component was just fine all by itself. And so that's something to understand about security flaws. And the problem of security at the design level is we can build these fantastic components that we intend to be used certain ways, like shoe component. Imagine we come up with shoe component. You know some jackass is going to use the shoe component to hammer in a nail. They are. They just are. And you can say, hey, I designed the shoe to go on your foot. Yeah, well, I nail like this, you know, whatever. Like, seriously, people will always screw it up. That's kind of what makes architecture a particularly hard challenge. And you know how architects get formed, right? You know, you're coding for years and years, and one day you're coding along and there's all these people following you and you're trying to run. You get one of those desks that you can like move, and there's like 20 people asking you stuff, and finally you just put down your keyboard and you pick up a magic marker and you never code again. You're an architect. It's so sad, but so true. Now imagine that you have to be one of those, and you also have to be sort of mean and evil and devious and a bad person, like security people are, you know. And then you see how rare people that can actually find flaws kind of, you know, it takes some skill. It takes a while to get enough experience to be able to do that. Which means we don't really need everybody to be able to do that, but we need more people than, say, 6 to be able to do that, which is a big problem. So let's talk about software security in general. You know, this is a book I wrote in 2006, which is now 12. It's almost ready to reach its teenage years. And it has 7 things, 7 kind of practices that you can add to your software development lifecycle. That's supposed to be, you know, some sort of a splooshy, DevOpsy, circular, who's he, what's it. You know, I'm not much of a software process person. You can do whatever process you want. But I am a software artifact person. Like, I'd like to see your code. Thanks, that's great. Just give me your code. Shut up. Just give me your code. It better build. Let me see your code, right? That was how I was in the early days. But I also want to see your design. And when you ask many teams, say, what's your design? They go, the design is the code. And you go, no, that's wrong. You know, the design, no, that's wrong. What is the design, and how do you write that down? And, you know, people have been taking a swag at this for forever. Grady Booch and the guys trying to do it with rational, and then they came up with the Ruppy thing, and then you got the, what do you call that big pile of goo that you're supposed to like figure out what the code does by looking at that? Okay, the code is the design in that case. But we have a problem because a lot of us really do use a magic marker and a whiteboard, and then we think about it that way. There's no way to formalize that enough to automatically visit it with some sort of checker thingy. So instead we have a human artifact that's pretty poorly understood in the first place by the person who wrote it down with a magic marker, and we have other smart people looking at that and trying to find problems in the system, and that's kind of one of the challenges. That's why bugs are easy. Code compiles, there it is, or it interprets, or whatever, and there it is, and we can do an analysis on it. Wow. Sure would be nice if model building and model checking, maybe formal verification stuff that we've known about since 1968 apparently, you know, that's the talk this morning. Maybe if we use some of that, that would be great, but we all work in the real world. So here's where we are. We're back there at, you know, architecture and design. What do the artifacts look like? How do we look at those artifacts? So here's the thing that we do at my company, and we actually I described this in chapter 6 of that book, Software Security. Has 3 parts. One part's obvious, got a list of known stuff, look at the list. Part 2 is pretty, 2 is the difficult one, and 3 is pretty easy too, know your dependencies. Although, let's see, microservices make for fewer dependencies, right? Is that right? Less databases, is that right? Yeah? Oh shit, that's going backwards. Right, so you know we're all like teetering on top of this pile of other people's stuff, and we're like, whoa! I hope they don't. Oh, they changed that one. Ah! You know. So from an architecture perspective, we're always like, ah! And somebody down there did a thing that was like, you used their shoe for a hammer, didn't you? But it was a micro hammer, so that's okay. Micro shoes, micro hammers. Maybe we should have shoes for each little toe. I don't know. So but the hard part I already described, which is system-specific attack stuff, ambiguity analysis, figuring out why 2 people look at the same thing and think it works in different ways. I'm not really going to talk about that, though. I just want to let you know that there are people that are trying to think about how to do this in a systematic way, and they're not making very much progress at all. So no magic way of doing architecture analysis. You might have heard of threat modeling. You might have read Adam Shostak's very good book on that. That's not how to do it either. I mean, we just haven't come up with it yet. I guess the first step is known attack analysis. Why don't we just like figure out what some known flaws look like and make sure we don't do the stuff we already know not to do. So that's what this work is about, at the heart of it. Avoiding 10 dumb things that you really should know not to do from an architecture perspective. And these are 10 dumb things that came from that collective I told you at the beginning of the talk. My buddies who I was like, dudes, we got to work on this flaw thing. Are you in? And they're like, is there bourbon? Yeah, okay, I'm coming. And the only rule was you have to bring flaws from your shop and you have to share them. So there were no lawyers involved. Nobody got permission to come to this meeting. We just sort of did it, which is how geeks get stuff done, right? That's how we get stuff done. And everybody dumped their flaws on the floor without any talk ahead of time about what constitutes a flaw. The cool thing was the piles sort of made sense. You know, we got the bulldozer out and we moved them around and we were like, wow, the guys at Google have very similar flaws to the guys at, you know, the Argentinian think tank. Wow, who would figure that? Which is interesting. So it means that, you know, collectively we do have some knowledge that's just smooshed in there somewhere. So let's cover these one at a time in the last 32 seconds of this talk. So number one, don't trust anybody, right? Now, the good news is that we're using fewer APIs than ever before. Right? So, you know, who's calling your API? Well, whose API are you calling? Well, you know, oh, are microservices going to help with this? Probably not. So you have to assume that that thing that you called is going to screw with you and send you the wrong stuff on purpose. Or maybe just take all the data that you sent to it and go, sorry, dude, I don't know what happened to that data. I just dropped it into the bucket. Right? So, I mean, these are things you got to think about. Do you trust all of the things that you're counting on out there? Who wrote them? Who gets to change them? What if a problem gets discovered in one? Or what if no problem gets discovered and they just rev it on you? And you had some assumptions about how it worked, and then one day it just stopped working. That never happens, does it? That never happens. Fortunately, software is so good that never happens. Right, so, you know, this is a biggie, this earn but never assume trust. Make sure that all the data from out there is not trusted, and assume that everything is a lie. Now, you know, this is the sort of thing that's difficult for developers, and here's why. You people are the most optimistic people on the whole planet. Like, so optimistic, you're so nice and so just like, shit, yeah, let's do it. Like somebody says, I've got the world's most impossible thing. It's going to take 20 trillion lines of code, and we've never done it before, but how about if you do it? And you're like, cool, I'm coding. That is unbelievable optimism. Like, seriously cool. But it also makes for surprises when it comes to security because, hey, there are bad humans. They do bad things on purpose, like rob banks with guns. The people that rob banks with guns also rob banks with computers. The gun is your code. Now you see what I'm talking about here, right? So, you know, we got to think about all this wonderful stuff in client code. I think my favorite problem that ever occurred was at some financial house where they had a super high net worth, ultra important database of assets associated with users. And then they had some client code that allowed you to check out your own account stuff. And so they shipped the entire database down to the client. Really? And then you type in your name and it would decrypt the whole frickin' database and give you your part. That is really bad design. We were like, cool, look, everybody's data. Okay, we're done with the analysis, gotta go. Number 2, use an authentication mechanism that can't be bypassed. Oh. Huh? It says 2, doesn't it? Let's go back. Ah, 2. Yeah, it's 2. I hope it's 2. I'm going to run out of time sooner. All right, so authentication mechanisms that cannot be bypassed. This is kind of important. You know, I already talked about the idea of, well, just be God. Don't even authenticate the user. We're sort of past that. Now we know that people that are probably not supposed to run our code might try, so we got to like make sure that they're people that are allowed to run our code. But, you know, finding out who somebody is tricky. And should it be a password? Should it be a thing they're carrying around? You know, can you get around that thing? There are all sorts of things that make very poor authentication mechanisms, like, say, IP numbers. That's a really bad one. MAC numbers, also bad, you know, but everybody's like, well, I can just use the IP number. You've never done that, have you? No. And, you know, there are 3 big tests, something you are, something you have, something you know. I'm sure you've heard of all these things. Here's a big problem with authentication mechanism. Often there's a way around them in your test harness. You people that do agile, super fast microservices development, DevOps-y, what's it called? Agile stuffs. You guys test first, right? Test first, code later. The test harness doesn't really authenticate all the time. That's bad. It's such a problem in hardware, including, say, medical devices, that there's often a way to short-circuit the test harness, the JTAG stuff, by physically destroying a link on the chip. And if you think about it, that's pretty cool. I think that's a good idea, but we really don't have a very similar conception in software land. And when we're doing super fast development, and we're doing test-driven development, which I think is a great thing, we sometimes forget that our test harness is also God. And one of the first things you try as an attacker is like, well, I'll just pretend to be from QA. Cool, not only can I hack them, I can also, check in the bugs in Jira. But I'm not going to set the security flag, no, because there isn't one. All right, here's number 3. It comes after 2. After you authenticate, now we know who somebody is, but we got to figure out what they're allowed to do. Because just because you're somebody doesn't mean you should be allowed to do everything. Or does it? Why not? It's better if everybody can do everything. No, wait, that's bad. So here's the funny thing. In security, they've talked about this thing called role-based access control for many, many years. You might have even heard of it, role-based access control, or RBAC, or the Bell-LaPadula model, which has all the peoples and all the stuffs, and you put a little check where the people are allowed to touch the stuffs. And the idea was, damn, that's a big matrix. I have 1 million users and 20 million microservices. More than yesterday. And so, now, I shouldn't be so bad. So now we got a really big matrix, and really big matrices are a bitch. They're just like, uh-oh, somebody got fired. What do? We got to change the matrix. Uh-oh, we added more services. What do? We got to change the matrix. So we thought, oh, maybe we'll just have roles. It'll be like developer guys, tester guys, vice presidents. They have access to nothing. Right? So, and you can change the access according to the role, but the problem is that in practice, role-based access control devolves to users again. That doesn't mean that this authorization problem went away. It just means that monkeys are bad at this, us being the monkeys. So the real question is, how do I compartmentalize? How do I test specifically whether that user can do a specific thing or not? And how can I do that in a consistent manner across my entire code base, right? So there's many things that you can screw up. You can look at those. The most common one is definitely the second, just forgetting to disallow somebody when they quit or they get fired, because nobody ever quits in software, do they? Your teams are always the same, like year to year. The waterfall model's great and all that. There's still people with clipboards and stuff. Okay, now we're on to number 4. Number 4, strictly separate data and control instructions and don't process control instructions from untrusted sources. Anybody ever read Smashing the Stack for Fun and Profit in here? No people. Dang, 1 people, yay. I just did a podcast with Aleph, with Elias Levy, that got published last week. So we talked about that paper which he wrote, and he was surprised as all hell that people, whoa, I just wrote a thing and everybody read it in security. The idea is that you can put stuff on the stack, and you can pop the stack, and then you can execute the stuff on the stack as code, which is super bad design. Super bad. That's what buffer overflows actually do. In some chipsets. Now, having a non-executable stack is one way to fix that. There are many ways to fix that. That's an old problem from the 90s. But it's indicative of this notion of mixing together data and control that really should be completely separated. There are ways that we can do that in memory, too. We can have some memory that's only for the stuff, and it's never supposed to execute. And if somebody tries to, execute that, the machine just says, that's not allowed to execute that. This is a portion of memory that you can't run as code, which is no fun because that takes your power away, right? But maybe we can utilize hardware to do some separation of code and data. Maybe we can have a compiler linker that does that somehow. Maybe we can, you can read all those things. the notion of making it so it's harder to code because you pulled apart control and data is a pain in the ass. And actually, it makes it harder to code, and you know, especially if you have to have super tight code. I don't remember what that is, but on an embedded device or something really small, like maybe an 8-bit microcontroller. And you're doing sneaky representation shenanigans to say, oh, that's a pointer. I mean, it's actually an array. Actually, I changed my mind. That's just a whole pile of memory. So, you know, in C, you can just say, hey, today I've decided that that's a whatever I cast it to. Bloing! Which is bad. And, you know, but C is like assembly language on steroids, dudes. Like, you want to get some shit done, just get right to the metal. Whoop! You control it all, so you can really screw it up. Right? So, you know, now when we get like meta-object protocols and stuff like this, you're like, is there a chip down there somewhere? Is there a chip down there? You just hear the echo, but nobody ever responds. That's when encapsulation works properly. So this commingling thing is a thing. The sea of bits is a huge problem. Type safety is good. Modern languages like Clojure, good. Bad old languages, bad. Okay. It's such an insightful talk, isn't it? Number 5, define an approach that ensures that all data are explicitly validated. This is very similar to number 1. You know, make sure you actually validate the data. Okay, let's talk about infinity. How many possible bad things can be thrown at your software? Infinity. Right. Should you try to make a list of all the bad things? No, that's infinity. It takes a long time to make that list. Really long time. Long time. Instead, you should have a list of stuff your program thinks is okay, and everything else gets dumped into dev null, right? So you have a white list, not a black list. You have one representational scheme. You don't allow strings. Strings are bad. Did I say that already? I meant to say that. Strings are bad. We're not going to talk about why. Okay. But look, this is something that everybody screws up. String functions were a huge problem and remain a huge problem in many C compilers do the wrong thing, and you can code yourself a big giant security hole, and the compiler will happily build you the code and give you an executable. That's a bummer. Like, I'm sort of bummed that that's still allowed. And you know, getS is a perfect example. Remember that from the very, very beginning? getS gets input until when? Until the attacker decides to hit return. Which is infinity. So you need a buffer that's like really, really big and keeps on growing forever, or else getS will always pop you, right? So there's certain things that just shouldn't be in programming languages, and I think we know better than that now. One time I was giving a talk, and Brian Kernighan was in the audience. We had a workshop on software security. I think it was all the software security people in the world in 2001, which was about 25 of us, the whole world. And Kernighan gave a great talk about super tight code, writing stuff for telephone switches, a lot of AT&T stuff. It was at Bell Labs. And it was a really good talk. And at the end, some smartass, that was not me, said, I just got one question, Brian. That was a great talk, really loved it. Who wrote those string functions in C? And he said, without batting an eyelash, oh, that was Dennis's code. Seriously, so later I was talking to Dennis, like, Brian said, you wrote that code. And he's like, no, that's Brian's code. You think we have a software security problem, guys? It's because that's other guy's code. Somebody else's code. Right, so, you know, blacklisting's better than, whitelisting's better than blacklisting. Say what you want to have come in, and don't try to list all the infinite number of bad things. Okay, number 6, crypto. Okay, here we go. Everybody's going to repeat after me. I can't do crypto. Are you ready? Here we go. I can't do crypto. Okay, that's all I have to say about this. You've heard don't roll your own. Don't roll your own. unless you're a real cryptographer, in which case you should not be coding. Believe me, because, you know, I've seen some Iran-Arrest code, and it's like, no. That's super bad code. So the problem is we have to have super good math and super good code at the same time. You can't do that. No one can do that. It's just super hard. There are a few people that can do it, but leave it to other people. And don't believe that you can come up with the brand new crypto algorithm all by yourself. No, but everybody tries it. Like, it seems so cool, and you're just like, I can do that. And then somebody reverses you with a pencil. That's how we popped Netscape. They had, you remember when you used to pop your mail? They had the thing, the password was crypted with an XOR thingy and a known key in it. And we did that with a pencil, seriously. And I had to call up my friend Norris Boyd at Netscape, which was this company, right? And say, dude, did you guys really use XOR? And he's like, who is this? I'm like, I was in your Boy Scout troop, man. So there you have it. Use crypto correctly. You can't do it, don't roll your own. Key management is a bitch. Oh man, you know what we're working on now? We're working on car security. There's lots of crypto on the buses, and you can make sure that only the authorized code gets to run and all this stuff. And how do you revoke a key on a platform that lasts 25 years? Nobody knows. We do not know. Like, we don't know. So we're just making shit up right now. Seriously. And we'll find out how we screwed it up later. Okay. Number 7. Some data are important. Other data are not important. All data are belong to us. Right? So this GDPR thing that they did in Europe, boy, was that great. It was so awesome. We're like, we can get the stuff done we want to get done. We'll just call it GDPR. We don't even know what that stands for. Who cares what it stands for? It stands for big pot of money to do whatever the hell you want to do. So we did that a lot. And that's very helpful. It makes people think about the data they're processing, the data that you're asking for, and the data that you're building. Let me tell you what. You people, all of you in this room, are more important to privacy on planet Earth than anybody else. Politicians don't matter. If you don't write the code, they cannot abuse it. So we have to be careful about what we write. Kent said this morning. It's super important that we think about the implications of what we are being asked to build from a privacy and a security perspective. Otherwise, we're going to end up with the marketing people deciding how to do privacy. No, thank you. No, 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 no. Or the politicians, and ours don't even have brains anymore, guys. Seriously, they have like mitochondrial growths coming out of their skull and a vacuous place where the brain used to be. All right, number 8, users. You know that famous old saw about how network people say, you know what, my network is great and everything's just hunky-dory until those users came along. I really don't like the users. That's what the network people say. They really do. They do that too. They really do. And then you really want to blow their mind, you go, we gave some of the users compilers. And they're like, because you're like a user with a compiler, that means you can build even more broken software, and this poor guy in network land's going to swing his arms till he starts to fly. Right, so think about user things like deployment. When should it happen? Like, obviously, continuously. And you should do lots of experiments at all times and then just roll back the security problems later. Never mind, that's a bad idea. Don't do that. You can't roll back a security problem that got exploited. So don't do that. Sorry, I have to compose myself. Security is a problem, though, because it's not like a magic, we can't put code in a magic box that goes, ding, everything's great, just run it, it's secure. Security is like quality. It's like reliability, it's like dependability, it's like all of the other ilities. It's an emergent property of the system. Like secure against what, for how long, what are you trying to secure? What are they trying to get? You got to think through all those things, because frankly, there is such a thing as too much security. Here it is. You like dig a hole that's 10 or 12 meters deep. I just said meters instead of feet. How's that? Pretty good. Yeah. Oh, thank you. But it's 10 or 12. I did say that too. So 10 or 12 meters deep, and then we take the computer and we like erase its hard drive. It doesn't have that anymore, does it? We remove the chips that are the hard drive and we destroy them with a hammer, and then we throw the computer in the hole and we fill it up with concrete. Now that is a very secure computer. It's also totally useless. So remember, at one end of security is totally useless. And at the other end is, sure, God could be able to do anything and no authentication required, right? And so we got to like balance that out. And the answer of how to balance that out, that's a design decision that you have to think about. And if you think about it explicitly, that's much better than sort of just, flarbing your way through. So we have to think about our users, we have to think about their culture, we have to think about whether people care about security. Guess what? No consumers care about security. They just think it is secure. That's the problem, because they think, oh yeah, they sold me a gizmo, a light bulb that's on the internet. I need that, I definitely need that. I need all sorts. I need more IP numbers, So Internet of Things, great. But now that we have all the things, like who's going to fix all those things? And they assume that the light bulb is secure because the light bulb uses crypto. Surely. Right, but the light bulb's not secure, and the light bulb's going to be in their house on their net, which is not sub-networked. I mean, it's like right naked. They have naked light bulbs with IP numbers in their house, and that's fine. But they thought it was secure, and you stuck your company's name on there. Like IKEA sold this light bulb. Now, when that light bulb gets used to hack the world, those people are going to be really mad. Even though you didn't say it's a secure light bulb, you just said, hey, it's a light bulb, whatever, dude. Buy it, throw it away, we don't care. You're just the consumer. But the consumers believe the stuff we're building is secure. That's because they're all on crack. They are. It's like our grandparents, the people that are running the United States now. Like those people, they're all on crack. And you can't explain to them that just because they bought it doesn't make it secure, so we need to make it secure? Wait a minute, I don't know. That's a very bad argument, but you know what I mean. So security's not a thing. We can't just sprinkle magic crypto fairy dust all over our code and everything will be shiny and sparkly and stuff. That doesn't work. We can put too much security. We got to think about use cases. End of life is an important thing. Let me repeat that. End of life is an important thing. End of life is an important thing. Sometimes you should kill your code. Like, you want to get rid of bugs? Delete code. Guaranteed to be removing bugs. And all you people are called developers, right? Any deleters in here? Look, there's one. Oh, there's a whole pile. There's a pack of deleters. Watch out. They're coming. It's like approaching from this flank. Deleters are good because deleters get rid of bugs for sure. All right, number 9, understand how integrating external components or microservices can change your attack surfaces every day at all times for no reason. Right, so anybody working on massively distributed cloud stuff in here? I mean, anybody not? Anybody got one core on their computer? Remember that? It used to have like a CPU, it was called. It was like one thing. You could like keep an eye on it. And often it would like overheat, so it couldn't do anything anyway. Now we have so much computing power, there's like extra stuff sloshing around. We don't even know what's running on our processors anymore. It's like, somebody ran something from Google? What the hell? How'd they get? Oh yeah, I told them yes, damn. All right, so so you can test your components for security. You can make sure that that shoe works as a hammer. You can include other people's components when you're reviewing. You can think about open source, who wrote that. You can keep an eye out for why the open source is broken today that guy wrote and nobody fixed yet. And these are all important things. In fact, knowing what your application or your software pile is important. That's half the battle. Most people have no frickin' idea how many dependencies they have. Like, try building with like not all the don't let the linker do its thing automatically. Just say, okay, try building with that. And you know how many times you'll have to try? Like 10,000. Because there's always some crap way over there that gets pulled in, and you're like, what does that do? Oh, I don't know. It doesn't build without it, though. Seriously. Seriously. In some shops, they have like magic include files. It's like, use the magic include file, it will always build. Well, what does it do? It includes everything. It's got a star. Takes a while to grab it all. All right, so composition is hard. Security risk can be inherited. Other people's code is going to break your stuff. Open source is not secure by default. Open source is not secure by default. Many eyeballs, total bullshit. Total bullshit, 100%. If anybody wants to fight about it, I'll fight you later after some beers, right? So don't trust until you've reviewed stuff. Like, don't believe that somebody who says they have a control built into their software really does. See if it works. Watch out for extra functionality, because no one would ever put Easter eggs in a thing, would ya? That wouldn't be fun or delightful. You're like going to show your spouse, like, look, honey, I put this into the TVs of everybody in America. It's kind of fun, but not good. Okay, so understand that. Number 10. Finally, the last one. I have 32 seconds, 28 seconds? 3 minutes, hot damn, I got some extra time in the bank. So be flexible when considering the future. Because I think Kent said it this morning, you can't really sort of know what's going to happen. You just have to build while this stuff is happening, and that's how you do the exploration part, right? We need to design for change. We already know that. Those of you who are thinking about microservices seriously know that you're doing that because change happens so damn fast. We can change little parts instead of big parts. That's why. There's a reason. So we have to have the right kind of sane balance there. We have to understand, isolation, turning things on and off, and whether we can swap a part out. I loved, there was a talk this morning, I can't remember what it was about the monolith, like avoiding the monolith. And the idea of like teeing the input and like saying, oh, well, that old legacy glob doesn't get to see that input anymore. Now it gets shuttled off to the new code. That's a pretty damn good idea. That's a really good idea from a security perspective too, because security is often about encapsulation. And encapsulation is really hard in a big, giant legacy code base with like all those mitochondrial tendrils running everywhere like Trump's brain, right? It's also, did I say Trump's brain? He doesn't have one, never mind, I take that back. It's also really hard when there are zillions of microservices that all talk to each other, because that's a network graph that's fully interconnected. And that's bad for encapsulation too. So you can't throw all of the encapsulation baby out with the we're going to be able to change anything hot swap on the fly without causing security trouble. So you should know that. Keeping secrets is hard. You can't do it. Somebody's going to leak your key. And then what? So, like, really seriously, how do you store crypto on a car that's going to last 25 years? Like, how? I don't know. We don't know. Right? So one day, something's going to break. The crypto's going to break. Somebody's going to figure out a new math thing. Quantum computing will actually become a real thing. It's not like ungodly expensive. And then all of the math that we're counting on for our crypto is going to be easy instead of hard. That's going to change everything. And we're going to have to be able to adapt. So our design, if it's set up for adaption, that's good. Adaption. Right, so remember, now that we know 10 things that we can look for, we can be super pleased to know that the number of potential flaws out there is much greater than 10. But at least we talked about 10. And these were not bugs. This is not SQL injection. This is not cross-site scripting hoo-ha. This is design issues. Design issues are important. We, in security, need your help in dev, and especially architecture, getting a handle on things like this, because we've not made near enough progress in the last 25 years on that stuff. So let me give you 2 pointers. There's some free stuff like Silver Bullet Podcast, which has Aleph on it, that just came out 2 days ago or something like that. And then there's my website, which people cribbed from to introduce me today. You're welcome to check that out. That's my actual email address. I would love to hear from you. You'll get a bounce back that says, McGraw is dead and he's somewhere else on Earth anyway. That's just a lie. That's for the vice presidents. Right? So if you're interested in security, if you want to talk about that stuff, I'm all ears. I've been working on this for 25 years, and I'm optimistic that we've made some progress, but we haven't made enough, and that's because we need your help. Done. Thank you.
Awesome. Thank you so